Um, so I do still get to keep my foot in shipbuilding even now because my day job is my VP position with Siemens Government Technologies, but I also have a role back on the commercial side of the business too as the global practice lead for shipbuilding. So I have a team of subject matter experts that work on our shipbuilding deployments all over the world and all of our accounts globally. So that's kind of my second job. But that's the part, you know, once you're in shipbuilding, you can never really get away from it. So keep coming back to that. Along the way, I did get a couple extra degrees. So a master's in ocean engineering from Virginia Tech and a master's in engineering management. So that's my work life. My better part of my life is my family, obviously. So I have a couple of pictures here of just my kids. My boys are 14, 12, and 10. And that keeps me pretty busy chasing them around to their sports and all their activities. And then my husband, we've been married 20 years, and he is a teacher by background, but now he works at a museum. So, so that's kind of the current state of things. And now I'll go back to how I got here in the first place. So how did I get to Michigan? I come from a really small town in Wisconsin, kind of in the middle of Wisconsin, but the good thing there is we're surrounded by water all the time. So we've got lakes everywhere. I had a lake in my backyard, and we had boats, you know, all different kinds of boats my childhood and growing up. So I knew I was interested in the water and being on the water and sailing and boating in general. But what we didn't have is engineers. So in my small town, I had no idea what engineering was. It wasn't really presented to me as a career option growing up, just because we just didn't have a lot of examples in that community. So didn't really know what it was. So what kind of started this journey for me was in 1989, I was in 8th grade, and the Michigan men's basketball team won the national championship. And my interest at the time was sports, really only sports, not school, not anything else, just sports. So especially basketball. So for me, that was like, I think I'll go to Michigan. And that's what I did. So that was in 8th grade. It just so happened my mom used to go to the Ann Arbor Art Fair every summer. So since she was going anyway, I was like, okay, I'm going to go check out Ann Arbor, check out the school, do a campus tour. So a couple of years later, I did that. And at the time, then I visited the engineering school and picked up a bunch of pamphlets. And one of them was describing the Naval Orchestration program. I thought, well, this is perfect. I'll do that. That's how I ended up in Naval Architecture at Michigan, and that's what led to my whole career since then. So, you know, just some of the best years of my life being there. So, I really, you know, appreciate again this chance to talk to you guys, and I know what a challenge it is. I know how hard it is, and it's worth it. So once I got to U of M, I definitely am the kind of person who pretty easily find myself overcommitted. So I joined everything I could. My philosophy, especially, I was out of state tuition. So I figured, okay, I'm going to max out this education and everything I possibly can, I'm going to get out of it. So I pretty much took 18 credits every semester, trying to get out in 4 years because I was paying too much, and which I did, which was also a challenge. But I also wanted to just make the most of the activities available. So I played on the water polo team, and I also was on the solar electric boat team coming out of the name department there. And we went and did competitions and designed and built that boat you see there. So just a lot of fun. I did a lot of other things too, but those were the two things that really stuck with me for the 4 years, and really were my kind of non-academic parts of my college experience that I really loved. And then of course, went to all the games, all the football games, all the basketball games, hockey games, everything I could do. So definitely appreciated my time there. And while I was overcommitted, I feel like the best thing about the engineering program there, but especially about naval architecture, just the ability to see across all the departments, all disciplines, it all comes together in one place. And most majors don't get to do that. It's a very, very special degree, but education program that really prepares you well for everything you experience after that, because you can really go in any direction. And that's what I did. So coming out of U of M, I had job offers in various directions. It's, I did consider going to grad school right away. That was one of the options, which I would have liked to do. But again, I had massive student loans and I had to figure out a way to start working right away and then go to grad school kind of in parallel. So my two favorite offers then were I had an offer from a shipyard, which I really would have enjoyed. Small shipyard, really would have gotten hands-on with all aspects of shipbuilding in that yard. And that sounded great. However, I would have had a real challenge to both pay my loan payments and also live. So my second offer that I preferred then was from Intergraph, which they at the time were hiring a bunch of naval architecture students. They actually hired 7 of us at the same time to go support the LPD 17 program at Avondale in New Orleans. And so that sounded like a great option to me. I could go live in New Orleans and work and then also go to grad school at UNO. It all tied together well. So I took that job and moved to Huntsville, Alabama to do my training, and then actually never ended up in New Orleans. I traveled there every week for about 1.5 years, but I actually ended up liking Huntsville and staying there. That was the headquarters of Intergraph. So about 1.5 years of that travel to work on Navy projects on our government side of Intergraph. And then they came to me and said, well, we've joined a consortium of global shipyards who've asked us to develop a new shipbuilding application. Do you want to do it? I said, absolutely. I would love to do that. So that's what I did for the next 18 years. And that team was actually headquartered in Hampton, Virginia. And so I relocated up there, moving from Alabama to Virginia to join that team. And there again, I encountered, as I joined that team, there were team members coming from Newport News Shipbuilding. These are the 4 shipyards in the consortium. Odense Steel Shipyard in Denmark, and Samsung Heavy Industries in Korea, and then Hitachi Zosen, which was in Japan. But the first thing I found when I walked in the door of that team office was Michigan Naval Architects. So it was, there were many Michigan Naval Architects in Newport News, and especially in the software division of Newport News. And so several of them had transferred over to be part of this team developing this new shipbuilding application too. So I worked with those guys then for the next 18 years and really learned a lot. And just the time we had together, just kind of that bond of having come out of that program and having that common educational base was really important to us and to our careers. So with Intergraph, I had a large variety of experiences, but most of them outside the US, just because Newport News did end up pulling out of that consortium when they went to model the Ford class aircraft carrier. They put in CATIA, a Dassault product to start with. So at that time, they kind of moved away from their involvement in this program. And so we worked with the other 3 yards. And so in that role or that capacity, I traveled all over the world, 1.3 million miles by age 40. So lots and lots of travel, and primarily to Asia. So Japan, Korea, China, Australia, Singapore, India. And then in Europe, my primary places were Denmark and Spain and Italy and France, and then Brazil, and then in Canada, Halifax. So all over the place, but not in the US at all. So while that was fun, it did get old after a while. And especially when I had the kids come along. There was a time when my husband was a teacher at the time, and so he took all of his summers off, and they came with me wherever I was. And so we spent a summer in Denmark and a summer in Japan when the kids were little babies. You can see one of the pictures there from us touring around Japan with them and strollers. But then as they got older, I found, well, it's getting harder for me to be away like 2 weeks out of the month, because that included the weekends too. So it started to get too much. And that's around the time I started looking for a job in the US, ideally nearby where I lived in Virginia. And I moved over to Siemens at that time. So that was 2017. But fortunately, I was able to find a similar role, still working in shipbuilding software. And, you know, I can say honestly, for 24 years, there hasn't been a single day where I didn't learn something new. The technical challenge is incredible. Just when you think you've mastered something, it changes, and there's constantly new technology coming. And not focus, you know, when I first started with my job at Intergraph, we were focused on CAD and CAE, but mostly CAD, so mostly design software. And now there's a far more focus on the life cycle of a ship and supporting the entire digital life of a ship, from basic design and simulation down through life cycle sustainment and maintenance. So think of the various software tools that are required to cover that entire life cycle of a ship. For, you know, in the case of an aircraft carrier class, it's 50 to 100 years. So a lot of technology needed to support that. So it's just been a constant learning experience and constant growth in technology knowledge, which has been really fun for me. So as I said, you know, the longer the life cycle, the more complexity and more data that's gonna come together in one place. And so the customers we support, especially that have those needs for long-term life cycle support, are commercial shipbuilders do, but the Navy in particular does, because they are managing change of a vessel across an entire class of ships. So that's where product lifecycle management comes in. And I'll talk a little bit about just the complexities of shipbuilding software and what we do and what we have to manage in terms of products and the complexity that goes along with those. But if you're wondering, like, how do you get from a naval architecture degree into software and the software, especially how do I apply those skills back to software? It overlaps significantly, just in terms of understanding how the ship is put together and built. And my areas of expertise in particular were on the manufacturing side of the ship life cycle. So production planning and manufacturing. I spent my early days even figuring out how to produce pin jig drawings and lofting documentation for manufacturing shell plates and you know, sizing pin jigs and that kind of thing. So a lot of that is now digital and modeled and simulated all in advance of when it's actually needed in the yard, producing computer-aided outputs for the manufacturing process. So my role now, though I still do own kind of the shipbuilding part of our business, it's expanded now to the whole DoD, so the aerospace and defense industry. So supporting the aircraft, the Air Force and Army accounts. The complexities are a lot different. So shipbuilding is much bigger. The products we produce are floating cities, whereas in aircraft, there's a lot more focus on electrical design and then simulation of everything that the aircraft does prior to it flying. All that occurs digitally now. So when we talk about digitalization and just what's changed, so as we moved from kind of a computer-aided design world into life cycle digitalization, the amount of data, and you guys see it, you see it every day, the amount of data available to you and that exists around the things that you use every day has grown exponentially beyond comprehension. So your car is collecting data, your phone is collecting data about you. Everything you do now is collected as data that's in the cloud somewhere and available to process. You have to know what you're looking for and you have to know what to do with it. So that's where digitalization comes in for shipbuilders and for the Navy and for our other Department of Defense customers. That's what they're looking for, an intelligent way to collect and analyze that data so they know what to do with it and can make good decisions. So starting with the basics of how we approach this process for shipbuilding specifically. So what I pointed out earlier is, you know, the benefit of a naval architecture view of the world, the degree you get crosses disciplines, it crosses every aspect of engineering. Everything you can do in engineering is covered in naval architecture. which is the interesting thing about it. You can kind of go in any direction and you're prepared for anything coming out of those doors. But if we start with just looking at the shipbuilding process and design process that we go through, we start with some basic modeling and design and bringing together the discipline and systems into a ship design. And that starts with just the general engineering process that used to be done on a drafting board and now is done in a computer system, so a software application. And everything from the shell expansion, the scaling drawings, all the hydrodynamic, hydrostatic calculations, all that's done by computer digitally now. All the design for the systems, model-based systems engineering, all that is done using those basic design capabilities. And what that allows you to do, having those models, is going to give you the ability to simulate and assess before you ever build or model or do any kind of tank testing and anything. You can simulate all that via digital technology now, and verify that your design is optimized the way you want it to be. And again, you're optimizing, you're simulating, you're bringing together your design to not only consider the ship you're building now, but the class of ships, and also taking information from the ship that's at sea now off of sensors and Internet of Things type technology that feeds analysis data back into the design process so that you can make design changes for future ships. And you'll see some of the industry needs driving that now. Business drivers are things like sustainability, environmental regulations and considerations. A lot of the ships that are already at sea are going to have to be modified to take into account the changes occurring now. So you feed the information from the ships you're sustaining back into the design cycle. You want to capture all that into your product models. So once you've got your design ready, your detailed design, your engineering process is starting to come to completion, then you start thinking about manufacturing and how to break that ship down into how it's going to be built and how it's going to be assembled in production planning. And this is where, in the commercial ship world, we kind of have two totally different perspectives. If you're in the Navy shipbuilding world versus in the commercial shipbuilding world, shipbuilding in Europe and commercially is very much focused on automation, robotics, designing ships that can be manufactured without as few humans as possible, trying to reduce cost and get the ships done as efficiently and quickly as possible. And what that means is in a place like Italy, where a cruise shipbuilder may have 10 shipyards at their disposal, you design a block of a ship to perform a certain way once it's built, but that block could be built in any one of the 10 shipyards, all which may have different crane capabilities, different welding techniques available to them, and different types of production capabilities, basically. So even though the block may be designed to its as-built condition, you have to consider the manufacturing processes that could be done in any one of those given places based on schedule or availability and capacity within those yards. So it means producing different deliverables, different outputs, depending on where that ship is going to be built and assembled. So the production process actually gets pretty complicated, and a lot of analytic algorithms go into calculating the best way to build the ship. Again, all done digitally. So then if you extend that ship into its life cycle, where now the owner operator takes control of the ship, whether that's a cruise ship operator or the Navy, they want data collected off the ship. They want to know the state it's in. They want to be able to update the model with changes that are made along the way, do inspections, and more importantly, do predictive analytics and maintenance planning so they can understand like when a part is going to break, when something's going to wear out, and then they schedule that maintenance in advance so they can get the ship in and out as quickly as possible. And this is currently a big topic. If you guys are familiar with the U.S. Navy's infrastructure and optimization work that they're doing, they're revamping the public shipyards and trying to reduce the amount of time a ship or a submarine is in port getting repairs. So increasing the operational availability, we call it. So we want to know as much as we can about what repairs the ship is going to need, so that we can plan those availabilities when they come into the shipyard and get them out much more quickly and back into the fleet, so that they're actually out doing the work they're supposed to be doing. So as much as we can, we pull the data off the ship, put it back into the model process, and really make it easier to capture all that digitally and make a decision. So we see the complexity increasing both within the military applications and also commercially, as the requirements change, and the commercial world is going to have to adapt to new requirements very quickly. On the Navy side of things, they have to do more work with a smaller fleet and really increase the amount of time a ship is at sea. So that means having as much data available at hand as for as long as that life cycle as we can. So if you look at the Ford-class aircraft carrier that's being built right now at Newport News, those are 3D modeled ships that they're able to produce without drawings. So all the production process is happening now with electronic work instructions that are telling the workers what to do without having to interpret the jobs off a drawing. So there's a lot of changes coming in terms of both the requirements for digitalization, but also with the data available to a much younger workforce who isn't schooled for decades in the process of reading and interpreting drawings. So a lot is changing, and will continue to change as more of this data and digitalization is available to the yards. So when we think about the digital shipyard and that life cycle that is processed from the acquisition process and contracts and requirements all the way down to what gets handed over to the owner operator as production deliverables, we have to capture all that data in a single place, which we call the product lifecycle management backbone. So for us, that's really the transition away from just the 3D CAD model into capturing every bit of data across the life cycle of a ship all in one place. So that can be anything from simulation data to potential like analytics data that you're pulling off a sensor as the ship's at sea, that everything needs to be stored in one place in order to really make good decisions and keep track of everything. So you'll hear the term digital twin, digital thread. So those are kind of the latest buzzwords. But what they mean is a digital thread, it captures information about a ship throughout its life cycle. It's not really a snapshot in time of data along the way. It's actually gathering all of that data together in one place. So your ship is going to look different as designed and as built and at sea, because 20 years into sailing at sea, you're going to be having a lot of changes made that make it look quite different than how it was designed. Especially when you think about swapping out weapon systems, crew capability and needs, things that change over the life cycle of a ship make it look a lot different than when it was built and delivered in the first place. So capturing all of that information in one place is what drives a digital twin and gives you the complete picture of that ship's entire life. And by the way, extending not just to a ship, but to a class of ships, which all have variations in slightly different designs. So when you hear the term digital thread, what that means for us is that digital twin, and then apply the processes and data that is applied to that digital twin along the way, the path of its life cycle. So what this life cycle is showing you is how the data kind of transfers across each process that occurs, but also different parties are going to be interested in different parts of this thread. So for example, if you're building a ship for the Navy is upfront on the acquisition side of things, is defining the requirements, The Navy's looking at design alternatives. They're assessing weapon system requirements. They're assessing what they need to acquire and setting the requirements for an OEM that's going to actually build the ship. So the OEM is responsible for the design process and driving out the data to meet those requirements. But then in the end, that same product is going to be handed back over to the Navy to maintain, run it and operate it and maintain it for the life cycle. So that same information gets passed back and forth between the Navy and the OEM at different points along the way. And in the meantime, everyone's looking at the same view of the data along the life cycle too. So it's all in one place. And that's where that PLM backbone comes in. So talking a little bit about requirements, because I think this is a particular area that's changing rapidly because of new considerations and regulations that are required for ships that are going out to sea now commercially. There's a lot more emphasis on requirements verification and validation upfront in the design process, and just ensuring that requirements continue to be met. And as requirements are changing, that information is getting driven back in to identify potential changes that may be needed. So a lot of focus on capturing requirements upfront and then validating to those requirements as you go. So where we see the PLM system sitting, and here again, I'm differentiating between the CAD design, which is like the 3D model of the ship, versus the backbone of information that kind of surrounds that model and is going to be used to sustain that life cycle. And the product lifecycle management is where you capture effectivity. So if you're building 5 ships in a class and each one of them has small variations, you don't want to copy that model and maintain it 5 times in the CAD system. You want to just identify what's changing on each of the 5 ships. It saves a tremendous amount of engineering time and also allows you to make a change once and propagate it through the different ships of the class. So that's where the PLM system comes in. So that is also going to be kind of the backbone or the tracker of all the information that goes along with that ship. So things like model-based systems engineering, analytics and requirements for the simulation processes that go on to that ship before it's built. All the information you're using to optimize the design and verify that you're meeting the requirements and in the best possible way, that can all get tracked and stored in one place. So when we think about ship design and the structure, the different disciplines that come into that, so structure, piping, outfitting, electrical is a key one of those things, but not even so much the cable systems that span the length of the ship. But think about now the chipset designs that go into making the ship electronics function, weapon systems. Those chips, like similar to what would be in your car now, are constantly changing and updating and capturing upgrades and changes that go on along the way. So that design process of chipsets is actually really critical to get into this process as well. So you see that's where we get away from like a traditional 3D model, CAD-based design, and into all the different design tasks that go on here, capturing data in one place. So those same chipsets are going to have software to drive them. And that software needs to be configured to work for the particular ship that you're working on. So you want to maintain the changes that occur to that software as well. So that's where it's like an application lifecycle management tool comes in. So specifically for software design and implementation. And then finally, you have your CAD. So everything comes together in one place, one single backbone of data. And this is what we term that digital thread, bringing everything together into one place. So what's kept me busy for the last 24 years is software for the shipbuilding industry is very complex. Same for aircraft design, same for automotive design, but in particular, shipbuilding has the biggest and the most complex models in existence of any product there is. And the amount of system interaction and the way the disciplines need to work together and be optimized in the performance of the ship itself, it makes it a very challenging environment to work in. So what is expected from the software industry then is applications that are purpose built for shipbuilding and function for that industry specifically. So you don't just take an AutoCAD and figure out how to model some 3D parts. It has to be actually purpose built for the shipbuilding industry. So highly configurable, just because every single shipyard does things differently, especially in the production practices and how they build the ship. And you have to be able to configure to that business process. Typically, a shipyard has been, some of them have been around for 100, 150 years, and their business processes are driven by environmental and geography concerns, where the shipyard's located, what kind of workforce they have, what kind of manufacturing capabilities they have. All those things are configurable or have to be built into that design tool that you use to drive out the design. So we also see a big move in the software industry to rapid development, agile processes, putting software more in the user's hands with low code, no code applications that let them actually configure and develop apps and do things that normally would have taken a computer science degree years ago. So those are some of the business challenges we see now, just in addition to the technology itself being complicated and changing very rapidly. But I'd say that the next set of complexities that we see are especially with the Navy pushing for kind of a cloud first deployment methodology. So they want not only the software used to design the ship in the cloud, but they also want the ships themselves to be capable of interpreting the data model and basically have a copy of the CAD model on the ship so they can make changes to it and assess the impacts of maintenance activities and changes as they go. So there's a big push to basically edge computing or pushing the software itself and the models themselves out onto the ships and out into the field. And that's going to enable more rapid decision making across the DoD. So other big challenges for us going forward, just in the software industry in general, are adapting to that, putting the software more in the hands of a younger workforce that is, maybe doesn't have the same level of industry experience, but is far more capable of technology and far more adaptable to be able to figure things out and solve problems in new ways. So those are some of the challenges we see going forward, and there's never a dull moment. I can tell you, it's been a super interesting place to be for my career, and my basis in naval architecture has been a tremendous tool to take me out into this field and just have that credibility and just the knowledge along the way to solve problems and do things like a naval architecture would. So I have appreciated every moment of that. All right, with that, I left some time for questions, so I will stop sharing here and just see if you guys have questions for me.
Okay, so here's a question from the back. So obviously, if a lot of this stuff started in the last 20 years or so, you must be importing things from like decades before that. So how so you come across a say Navy combatant that's been out at sea for 4 decades. How do you get started on that? Since everything, of course, would have been entirely on paper if it even existed at all.
Yeah, and in fact, it's a good point. And in fact, there's not even paper for a lot of that, because the drawing
systems are made in the yard. We're welding this to that.
Yeah. Yeah, so the starting point for most operations today, for repair operations and maintenance, is actually scan data. So taking a laser scanner out into the field or into the yard and scanning what you have there as a base. And then that scan data could actually be imported into a 3D model, and then you kind of can make your modifications and your changes from that starting point. So the scan data has come a long way. It used to be real faceted and real difficult to interpret and work with, but now it's come to the point where they can basically render those scanned models pretty accurately, and then the point where you can pull dimensions and measurements off of them and use that data. All right, so just to wrap up, I really appreciate you guys' time today. I hope this subject is interesting for you. I can certainly take questions after the fact. Just get in touch with me, and people there have my contact information. So reach out anytime with questions and anything you think of, and I'm happy to talk anytime. Thank you.
Thank you, Kristin.